like I said, here we go. Video. Okay, so what did you guys say the reaction, the reactants were for aluminum, the synthesis of aluminum oxide and water? We should all have that reaction. O3, so that's aluminum oxide. H2O yields aluminum hydroxide, right? That's one of the syntheses reactions with water, so you should know how to do that part. That 1 to 3 to 2 ratio. Then the next part, and if it helps you to like highlight to figure out what the givens are and what the questions are, do that. But the first question required you to see how many moles of aluminum oxide were formed from 98.0 grams of aluminum oxide. So if you need to write this down right now, write it down. But I mean, you may not get the entire the process down, but you can at least write down some information. You take your grams of aluminum oxide, you went to moles. You went from moles to moles of aluminum hydroxide from the BCE mole ratio. Now, if your BCE was incorrect, that step right there is the only step that should be a necessary one to change. And then at the end, you should round it to 3 sig figs, so 1.92 moles of aluminum hydroxide. Who got that? Woo! All right. So the whole excess water thing is irrelevant right now, so I just am highlighting the really two important variables given to us. So the second question said how many moles of water are needed to react with X number of moles of aluminum oxide. Well, we're going from moles of aluminum oxide to moles of water. How many steps does that take? One step. You're using mole ratios. That's it. So whenever you set it up, you have to pull from the BCE the coefficients, but that's the only step that's needed to get to 1.10 moles of water. 3 sig figs in that one. Who got that? Woo! Okay. And then the next one, how many grams of product? You're like, oh, this mysterious product. You know what the product is. It's aluminum hydroxide. It's formed from 67.2 grams of aluminum oxide. So we're starting with grams of a reactant. How do we get to grams of product? Grams of reactant to moles of that reactant, and then moles of that reactant to moles of that product, that aluminum hydroxide, and then moles of that product to grams. So there's like a couple steps, but you know your process now. It's just tedious at times, so I'm trying to figure out where to cut down some of your problems. Yesterday I actually had 8 problems. I got down to 4. Some of you guys did 2. I have 8. That's 25%. So I try to alleviate the time, but some of us still didn't get to it. So the final answer on this one is 103 grams after you round it to appropriate sig figs. Who got that? Woo! Okay, so some of us are 10 for 10 right now. All right, so that's the process. The next one is more difficult. That's the one I actually want to spend some time on. So this one, we also got the BCE right because I think we wrote it down. Did we write this one down yesterday, the BCE? Yeah, we knew that barium sulfate was our precipitate because we know some of our solubility rules. I'm sorry I don't have the little cards out for you, but sulfates are insoluble. Sulfates are soluble except for CBS, barium, strontium, and calcium. So this was the one where I told you had this special new unit called molarity. Molarity. Molarity is moles per liter. Number of moles. So if I give you a number for the molarity, that is the number of moles. And that's a conversion factor. So just like any conversion factor, it's a fraction, right? Does the fraction have to stay like that, or can you flip it? A conversion factor is malleable, right? You can flip it, do what you need to with it. And that's really valuable in thinking part B of this one. So I circled my 2 givens. Now these 2 givens were about the same reactant. That's why I know I had to do M times V to give me moles of that particular reactant, sodium sulfate. So the question said, how many grams of precipitate will form? So this one's a hard one because you have to figure out who the precipitate is first. Grams of barium sulfate is what the question was about. So I showed you this part yesterday where you had to take your liters times your molarity, moles over liters cancel to give you moles of sodium sulfate. We got that far. But then the question says to go farther, so from there you should have gone to moles of barium sulfate, canceling out. Where did we get these ones and ones from? The mole ratio, and then we had to just go to grams of the barium sulfate with molar mass. So you should have gotten 0.28 grams of barium sulfate. You got that? Woo! This number? This was just barium plus sulfur plus fraction. The molar mass by adding it up. Okay? So I think some of us got that, but you guys see that just this new piece of information here can just be combined to find moles. That's really the only new step. Now the next one is requiring you to go a little more in depth in what is molarity, what does it mean. So same story, you're given volume and molarity, What automatically do you think you should do with those? We have milliliters and molarity. So milliliters are useless. Change the liters, and then times it by molarity, and what do you get? What unit? Moles, right? Moles of sodium sulfate in this case. Our question is to go to something about barium nitrate. It's actually the volume of barium nitrate. And that last part is kind of hard to understand. But if we have moles of sodium sulfate, I know I got to get out of sodium sulfate. So how do I get from sodium sulfate to barium nitrate? Ratio, mole ratio, right? So now I'm in moles of barium nitrate. Then you're given a third variable. You're given that third given. 0.1 molar barium nitrate. So I'm going to show you my work, but it's all together. I didn't stop once to stop and get moles. I just kept going throughout the conversions. So I want to show you where you could have stopped. So looking here, so again we have M times V. So here's my V, but in 50 milliliters in liter form. My molarity of moles per liter, and this is of sodium sulfate. And just like you told me, that got me to moles. But I don't have to stop at moles. I can just keep proceeding through my stoichiometry. And this mole ratio came from where? 1 to 1. The equation BCE, right? And that gets me to moles of barium nitrate. But then a lot of us got stuck there, like, what do I do with that afterwards? Well, if the question really is asking for liters or milliliters or volume of some form, then that actually means you can use the molarity, but if you flip it, that's going to get volume on top. So then I took this M over V, or M over liters, and I just turned it upside down. Why is that beneficial? Then the moles and moles cancel, right? So it's just molarity flipped over so that you can cancel out moles of barium nitrate. And then that number was given to me. I didn't make that number up. That number was given to me per 1 liter of solution. But then the final answer is supposed to be in milliliters. So what do you think my last step was? After this step. Back to milliliters. And what's that conversion? Per 1 liter. Right. So that's my last step there. Liters cancels. It gets me 500 milliliters. I saw a couple people had that. Who had that? Okay. Promise. I didn't see like 3 people. Okay. Good. So that was this new part right here. This is the only new thing that we didn't talk about yesterday. That it's a conversion factor. You can flip it. Does that make sense though? Those of you who are like, aha, yeah? Do we have aha moments? Some of yours are like dead to the world, so okay. It's like 3rd period, right? We've been doing this for a little while, okay. So last one, how many, starting with 2.5 moles of precipitate, how many grams of the other product are made? How do you guys start on this one? Of what? Anybody? 2.5 moles of barium sulfate, and you went from moles of barium sulfate to sodium nitrate, which is the other product, and then moles of sodium nitrate to grams. So it's just a 2-step process, 2 conversion process. This one was probably, if you got stuck on B, you should have dropped down to part C, because you totally could do this one. This one's not really new at all. It's moles, and then where did we get this ratio? Equation BCE, right? And then grams of sodium nitrate, which is its molar mass. Just calculate it, and then 425 grams of sodium nitrate. Who got that? Woo! Okay. So if we need to kind of turn that stuff in tomorrow because we need some extra time on it, that's fine. While you're looking at that, pull back out your percent yield notes that you just wrote down. We're gonna do a problem with that. I didn't do that yesterday, so I'm gonna give you guys 45 minutes of practice. So I hope that helped for some of us. And then I gotta go grab something you stole from me because I want to show you guys something in a minute. Okay, we got this down, right? Do you remember this from your reading guide 12, which I'll hand back as soon as I can? Yeah? Percent yield. And what kind of stuck out to you here? What are some interesting terms and definitions? Huh? In the land of make-believe, we have this theoretical yield that if I was a perfect chemist, I would be able to be perfect in all ways and get exactly the amount of product that I, from reactants that I put in. We put in reactants, we get products, right? If everything in there happened perfectly, then that entire reaction in the lab, me massing stuff out, me pouring things between graduated cylinders, me evaporating something, whatever I'm doing, precipitating something out, if I was perfect in all ways, I would get this theoretical yield of a product. So remember, yield is always referring to products. You yield products, you don't yield reactants. So that's in the land of make-believe, that's la-la land. We will never get perfect yield, but we always compare what we get to what we should have been able to get, because we're comparing to what we possibly could get. So what actual yield means is actually what you get in lab. What is gotten in the lab. So in a question that's referring to percent yield, do you think I'm going to make you get up in the middle of the class and go, okay guys, let's go figure out what we can get in grams of yield to get the actual yield? Probably not. Like in a lab situation, I'd say, okay, what's your actual yield? So I'm always going to give this to you in the problem, because I'm not going to make you get up in the middle of the problem and go, oh, let me go see how much I can make real fast and get an actual yield, because that would just be too long. But in the lab, we will get some actual yield, and we'll compare it to theoretical yield. So this is what we're actually going to get in the lab. So you have to do differences. La La Land, real stuff. So using that information, percent yield, what does percent refer to? Usually when you do percents, what are you comparing? Okay, we're going to be comparing actual versus theoretical, and then percents always make you do what mathematically? Times 100, right? So percent yield is going to compare these two, and we're going to times it by 100 to see what percent yield we had, to see how awesome chemists we were, right? So whenever you calculate percent yield, the two yields must be the same unit, but your unit can be pretty much anything. They can both be in moles, they can both be in grams, or they can both be in liters. Real fast. Okay, so actual yield over theoretical yield. How do I remember this? AY over TY. Alphabetical order, right? A over T. Can't mess it up. I have a joke for you. Because in chemistry, we don't always get great yield. But what do you think of percent yield? What percent yield do you think is a good yield? Give me a number. 15% yield? That's crap. That's awful. Like what? 99% yield. That would be amazing. In AP chemistry, I always ask, I reward them for getting the best percent yield. They get more money. And that's because I want them to be very, very good in their techniques and very analytical. So generally, like 85% yield and up is like baller. Okay, down less than that means we made a mistake, a big mistake. Sometimes we spill all of our crystals and we lose everything. So the joke is, no, the next joke. I'm a boss at purifying, but he only gets 9.63% yield, right? That's really crappy. And then this is what we do: lab grade based on percent yield. Spend an hour pathetically scraping every last grain of product off the glassware table and floor. Sorry, that made me laugh. Because in AP chemistry, they're like scraping their crystals off because they want to get their mole money. So I'm going to show that to them. I just found that. I'm rolling inside. You'll understand one day. So anyway. Back to the question. Whenever we have information, sorry, inside I'm still laughing because they're like scraping their crystals off to get the percent yield. Anyway, what is the percent yield? So question, percent yield. What does that mean? We really, really actually have to calculate. Okay. Actual yield over theoretical yield times 100. That's our question. When 14 grams of magnesium chlorate decomposes. Okay, so that's a little bit of extra information. And 3 liters of gas are collected, okay, at STP. Okay, we actually have a lot of information here. So instead of reading that problem, I'm writing down all my givens. So my question is actual yield over theoretical yield times 100. My first piece of information is 14 grams of what's magnesium chlorate? Mg. ClO 3, 2, parentheses 2. All right, so that's our first given. It's decomposing, right? So what do you think we're probably going to be writing now? The VCE? Yeah, VCE. So before you even move on, I'm just going to go ahead and I know I have to write this VCE. How do chlorates decompose? Oxygen, right. What other product? Magnesium chloride. How do I write that? You guys are really good at predicting products. Better than like half my AP students. All right, so balance. 3 on the oxygen. I heard you. Anything else? No? M1, Cl2, Cl2. We're good. Okay, so now let's finish reading the problem. All right, so that decomposes and 3 liters of gas are collected. Well, what is that gas now? We know it. We know it. Yeah, we got 3 liters of oxygen gas is collected. What do you think that is in my question? That's what? That's the actual yield. It's given to me because I can't make you guys go up and like, all right, let's go decompose some magnesium chlorate. That's the actual yield. So just label that AY so you remember, because I gave it to you. I have to give it to you because I'm not going to make you go to the middle of the class and do the lab. Okay, it's collected at STP. So I'll just write STP here. Is there anything that's significant at STP that we know? Maybe a conversion? Okay, so maybe we need to use the 22.4 liters of gas per mole. And why are we allowed to use this one? It's because it's for a gas. We're talking about gases right now. Okay, so this is the actual yield. We know the units have to be exactly the same for theoretical yield. So what are we looking for? What units are we looking for? Okay, so the question is liters of oxygen, and that's going to give us theoretical yield once we get there. So this one's a puzzle. We had to kind of break the puzzle down. We're going to put it back together. What number do you think I have to start with? No, the 14. This is my actual true given. That's what I'm going to start with. This is something I'm going to compare at the very end. I actually wrote it in green so you could see there's a difference here. So the 14 grams of magnesium chloride is what I'm starting with. So using all that information, 14 grams of Mg ClO3 2 is my starting point. What do I have to do? Yeah.
Your theoretical yield, the liters of MgCl.
No, my theoretical yield has to be exactly what my actual yields units are. So this one said I actually yield 3 liters of gas. So I'm going to find from this is a solid. I'm going to find the gas that it can create. So I'm going to use mole ratios to figure out from this to this. Let me see if it clicks as I go through. Okay, so if I'm starting with grams of chlorate, what do I need to do? You're right, there's only one thing to do. Your question is to go to mole. So what's that molar mass? Anybody? Calculators out? At least? Magnesium weighs 24.31 plus how many chlorines? 2, so 2 times 35.45 plus how many oxygens? 6 times 16. What'd you get? 191.21 grams of magnesium chlorate. Okay, so now we've got moles of magnesium chlorate. Well, that's still not oxygen gas, right? We have to get to oxygen gas to compare. So how do I get there? Anybody? Ratio, thank you. So I have a 1 to 3, so what's going on top? Or what goes on bottom? Either way. What do I have to cancel? What? So the 1 magnesium chloride on bottom, so 1 magnesium chlorate on bottom. And what goes on top? 3 moles of oxygen, because that's what the BCE said, according to us here, 1 to 3. Okay, now I'm in moles of oxygen. I'm almost to a usable unit. Remember, I have to compare exact units. Say exactly the same units, or what's my last step? Right, 22.4 liters of oxygen per 1 mole of oxygen. And that's just going to get us to liters of oxygen. This is theoretical yield. So in La La Land, if I had 14 grams of magnesium chlorate and I decomposed it and it made all the gas it was supposed to make, this is how much gas it should make in La La Land. What's that answer? 4.9 liters of O2. Okay, so what do you notice the differences between actual yield and theoretical yield are? Okay, we're not perfect, right? So what do you notice about actual yield? It's less. Okay, always, like 99.99% of the time, this one is going to be more because you're happy and you make it perfectly. It's all good, right? So you're going to have 4.9 here. And we're not perfect, you know, in the real world, it's actually less than that because we just can't get an efficient yield. So then how do you get percent yield? Okay, I hear you. 3 liters divided by, and what you got?
61.
So what would you grade them? What would you say about that person? Bad yield, shame, right? Not a very, they didn't really do a great job of capturing all the gas or whatever it was that they had to do. Okay, so that's new, cool stuff. I have more new stuff for you. I'm going to make some gas. Goggles. So, ooh, I could grab a beaker. How do you grab me a small beaker with water? Like a 50 or 100. I know this is smaller. A 50 or 100. So, it's getting to be a holiday. I call it a holiday. Soon, because it's the day before my birthday. Start celebrating candy early. Yep, it's just like halfway.
Oh, yeah.
Okay. I'll be 16. Same.
Can we sing happy birthday to you?
Only if you can sing it like they do the Mexican restaurant.
Oh, well, you know what?
Yeah. Okay, so we have a reaction. I'm going to try to do this twice. This is calcium carbide. When it reacts with water, it makes acetylene gas. You guys are hungry. Yeah. You guys are fine. You guys are fine. Just stand to the side. So I'm going to start making some gas as soon as I drop it in the water. You listen really closely. You can hear it bubbling. Maybe not. It's bubbling. Just believe me. Okay? So if somebody push your precious papers to the side, I wouldn't want anything to happen to them. Okay, let me just give it one more second. Right, and acetylene gas is flammable, combustible, whatever. Okay, here we go. Whatever happens, happens. Woo! So, did his face pop out?
Yeah.
Not yet. Where's the eye at, guys? Oh, it's right there. Okay, pass me the eye back. We're going to do this again.
Oh, okay. I did not know.
Okay, this one eye, man, it doesn't like this. Okay, so he's got a little sneaky grin on here. What'd you just drop? As long as it's not the phone, it's just a calculator. Let me put one more here for the road. All right. So let's see what else we can make here. All right. So give me countdown from 10. 9, 8, 7, 6, 5, 4, 3, 2, 1. That was a poopy one. Okay, so I'm gonna let it build up to some more, and I'll do another piece because I reused the water and it was already done. So I'll do it again at the end, okay? All right. That first one, that project is gonna come out at you guys. So, let me see here. Can I get a volunteer?
I got you.
Ooh,
No, I can't make
ooh. Who can make sandwiches? All right, Jason.
I'm a pro.
I'm pretty sure
Can you make sandwiches?
I'm a pro grilled cheese.
All right, we need a grill here. We need a grill. It's already fit. Oh, I didn't mean to do that. Sorry.
You can bake. I'm willing to JD.
Wait, are we
Sorry. We're making peanut butter and jelly. You see? This is like that diet bread. You have diet bread? Ew. That diet peanut butter, that new PB powder, blend it out for us. And then that sugar-free jelly. There we go. All right, so hold on. What is the recipe for the perfect PB&J?
Peanut butter.
Okay, but how many?
Two slices of bread.
So 2 pieces of bread. Okay, you got this. 2 pieces of bread. And then what else? So like 1 piece of peanut butter? Like a piece of peanut butter?
Ah,
Yeah.
you gotta spread it. You gotta
And then
spread it
like,
with the
then like a piece of jelly.
jelly. You gotta spread it.
Okay. Well, we are to the consensus. You need 2 pieces of peanut butter, a piece of, 2 pieces of bread, a piece of peanut butter, and a piece of jelly, according to Miss Emma's recipe. All right? And you got this?
Sure.
I believe in you. Make sandwiches. Go. Hurry. Go. Go. We're timing ourselves. This is a reaction. It's gotta go fast.
Gotcha.
And we're your cheerleaders.
Make them roll.
Okay. 1. Woo! 1. Let's go, man. Let's
Don't listen to
go.
what they tell you.
2.
Make sandwiches.
2. 3. Woo! Yes, go. 4. 4. Yeah. No.
Not at all.
So what, guys? What just happened? Oh, we ran out of bread. We ran out of bread.
Limited Reagent.
So what made us stop making sandwiches? No, it's gotta be a full sandwich. We don't do that half stuff. Okay. So we ran out of bread. We have limiting bread.
That's
We
that's
have,
that first slice that nobody uses.
and then what do we have with this? Excess peanut butter and jelly, so we can eat this peanut butter and jelly. I'm cool with that. But excess and limiting. Ta-da! Limiting food. So, in a reaction, what we assume is usually going to be present. Something's going to be in limiting and something's going to be in excess. Ta-da! Okay, while you're doing that, I'm going to try this again, but it may be all fused out. Just shield your face. Wait. I don't know. There's no promises here. This may have already like diffused out. Wait. 3, 2, 1. So, both eyes! Woo! Both eyes! Alright, this is settling gas I'm not supposed to be breathing in, so I'm gonna go ahead and like put this in the back. Okay. I will do it again. Alright, start writing down those notes.
Ms. Emma, could I please have Rebecca Lindgren for dismissal?
Yes.
Thank you.
Shame. Okay. Thanks, Miss Emma. We're writing down our notes now. No problem, guys. My duty is to entertain and teach occasionally. Don't tell fourth period. Oh, it's already on Snapchat.
No, it's not because they blocked the Wi-Fi.
Oh, thinkers right there. The video is going. Okay, you will make out the video questions and. So this is called limiting reagent, aka limiting reactant. A reagent is a reactant. There are no differences. It's just the way we say it for some reason. Reactant. So guess what? An excess reagent is an excess reactant. It's the same word. And I will probably always abbreviate it now. LR for limiting, and then XS for excess. Yeah?
Yeah.
Excess for excess. And I'm going to teach you one method to it, and I'm going to try to show you how to organize the information. And I asked my AP class, because they remember learning this, and we wrote it a slightly new way in AP. They told me to show you both, because I think some of you guys are like ones, and you guys are like another. So I'm going to pull them together here. Oh, and thank you for some of you guys for bringing in s'mores ingredients. If you guys, we're going to do that hopefully Friday. So that means tomorrow bring in some stuff if you would like to. Some of us are going to do it in groups. Some of us are going to share the class. So I'm not demanding it be shared with the class, but I'm asking for it. Yeah.
Is there any like thing that we need more than the other?
So you're saying like, do we have excess of something?
Yes.
I would check. We always, the limiting reagent's always chocolate,
Yeah.
because that's usually the favorite. So if you can bring in that, would be great. I'll get it soon, okay? Alright, take another couple seconds here. We're going to do some examples. And the examples mean, they walk through these steps, so it's really going to be valuable to have a couple of examples for tonight. Yay!
Rebecca lingering.
She just.
Did she just?
So many L's, man.
I was just gonna say that. Annabella.
That's so cool.
Max. Oh. Divine Patterson.
Okay.
And Gwen.
And then we're doing one, two, Thomas, not that bad. Yeah. Okay, and great, let's do this. Oh, here is another food example. You know me and my food examples.
Nice.
What was the limit? What were the excess reagents here? We had a lot of extra cheese. We had one extra tomato, and we had one extra bun. So what was the LR? The hamburger or the veggie burger. You just went straight for hamburger. It was a veggie burger. Okay, so this is going to be the marathon for today. Okay, this one's going to be a long problem. Full sheet of paper for it. Okay, we are going to work through our steps the same way we went through yesterday, except now we are actually given information about not only one reactant but two reactants. That's the choice now. Whenever you are given two reactants, your choice is to figure out who do I use to control the amount of products made. Because remember, whenever you're calculating, you have to consider really only the limiting reagent or reactant, because that's going to force the products to stop forming. So that's the one reactant that's important to make sure that you use when calculating products formed. So the first step is going to be figuring who the LR is. The second step is going to be using that information to proceed with the problem. So before we can do that, though, we got to write down our BCE. So you guys start. Oh, you guys start by writing the BCE first. Read. Reactants are. Yep. Your reactants are. I heard FE.
Plus C.
Okay, what does that yield? Fe NO3, and I will tell you the charge of iron is 3
Plus
copper solid. Huh?
Fancy.
Yes, I know. I'm trying to go more fancy. It's a little neater too. So when we have this reaction, now we have to balance it. Give me the balance. Sorry, I'm trying not to move slow. You guys have calculators ready. We're going here. Oops. And a 3 in front of each copper. This one, I told you iron was a 3. I didn't say it in the problem. Iron is a 3. It generally does from a 3 charge. Okay, so now we got to read the question. We have 3.6 grams of iron. That's information about one reactant. And it's reacting with 5 milliliters of a 0.51 molar solution of copper 2 nitrate. So again, it's very explicit that it's an LR problem because it's giving you reactant information about one and reactant information about another. That's when you have to compare them. So this one first requires us to take 3.60 grams of iron. And do you guys see, well, on your step-by-step process, what did it say you to do next?
Oh.
Compare so do what with them? convert them both to moles first. Okay, so that's what I'm doing right here. So what's my molar mass of iron? Calculator out. What's my molar mass of iron?
55.85.
Okay, so 1 mole of iron is 55.85 grams. And that is, I'm calculating with you, so I'm giving you time to kind of calculate. What you got? I'm going to go 446. So it's 58. I'm just going to round up to 6, just so we have some extra decimals here. All right, so this is literally how much I have of this reactant. So above that, put have in capital letters so that you remember that's what you have of that reactant, one reactant. Same thing on the second one, but how do we convert that information to moles? How do we convert that information here to moles? Times them, but what does the first one have to be in? Liters, all right? So second reactant, how do you, go ahead and tell me that in liters. 0.0050 liters of that solution times, how do I write molarity? So tell me the units. It's, so I hear you 0.51 what? Moles of copper 2 sulfate, or nitrate, sorry, copper 2 nitrate, over what? 1 liter of solution. Okay, so now this is where liters and liters cancel, and that gets me directly to moles of copper 2 nitrate. So what is that? Two by 5?
Yep.
Moles of copper 2 nitrate. And again, this is how much I have of this one. Box them off or something, because you're going to have a lot of work on your paper and you're going to not know what's what at the end. Okay, so if I have this much of each of them, and I know the recipe in which they react, the recipe is I need 2 irons and 3 copper 2 nitrates to react to make products, right? So here's how I compare them. I compare them by multiplying them by each other's mole ratios. So basically what I'm going to do is say, let's just say, for example, if I had 2 moles of iron, how much copper 2 nitrate would I need to fully react all that iron? 3, right? So if I had 1 mole of iron, how much total copper 2 nitrate would I need to react with it? 1.5, right? So I'm using the ratios to figure out how much I need of the other one. But this is a weird number. I can't do that in my head, so I'm actually going to write it down. So I'm going to multiply by the ratio of 3 on top, so 3, and I'm going to squeeze it in here, 3 moles of copper 2 nitrate over 2 irons. And this is just me writing it down because I can't do that math really well in my head. I can multiply by 1.5, or I can multiply by 2 over 3 in my head, but not with this really tiny number. So this is going to be how much I need of the other reactant. So tell me what that is when you get there. Point 9669 moles of copper 2 nitrate, because that's what's on top, right? Sorry, I'm out of space, so it's looking weird right here. But I basically converted from the moles of iron I had, I multiplied by the mole ratios, and I said that's how much copper 2 nitrate I need to fully react with all that iron. So if that's how much I need, compare that to how much I have. Do I have enough copper 2 nitrate to fully react? No, I've got way less copper 2 nitrate. I need a ton more. I have very little. So what can you imagine? Yeah.
I'll put that in the calculator. I got 0.09.
I actually did too. I didn't look at my calculator. 0.09. Okay, but still same story stands. I need more than I have. So what can you assume about copper 2 nitrate? It's the limiting one. It's going to run out first. So it's the LR. So what can you imagine about the other one? It's the excess. So all I did was visually compare the amount I need to the amount I have. I have way too little. I need a lot more. Ain't gonna happen. It's gonna run out first. So this one right here is my LR. This one is my excess. Label it on your BCE because you're gonna forget what you just came to the conclusion. So what's the answer to part A? Copper 2 nitrate, thank you. Copper 2 nitrate is the LR. Okay, so we just did all that mess to figure out what the LR was. Now that we know who your LR is, we are going to start with the number of moles. So part B, start with moles of LR, and that's how you proceed with the problem. So how many moles of LR do we have? You labeled it have, thank you, 0.00255 moles. That's how much you have of it. That's how much you needed of it. That's how much you actually have of it. So that's what we're starting with, moles of copper 2 nitrate. Let me get my fancy pen back. So what's my question part B? Sorry, I'm scrolling around here. What's my question part B? How much copper will precipitate from the reaction? So question, grams of copper. You can get me there. That's my first step. Okay, do mole ratio from copper to nitrate to what? To copper. You guys have your BC in front of you. Mine's way up high. What is the ratio? 3 to 3. 3 moles of copper to 3 moles of copper to nitrate. I like my handwriting with this pen. Okay. All right, cool. I'm in moles of copper. Question again is grams of copper. What are you looking at?
Say grams of copper.
What you looking at?
The grams of copper is
The PTOE. You're looking at the molar mass.
63.50.
Okay, and how much you get. And I'm only doing one of these problems because they are long. And once you get the process is a process.
I got 0.162.
So 0.162 grams of copper. That's how much will precipitate out. Yep, you would mass that, you'd figure out how much precipitated out. And you know, your units do cancel here and here and here and here. I'm not canceling, I'm not showing the cancellation. Okay, so that's part B. And again, once we figure out the LR is, we always start with the LR amount and then move from there, because that's showing the control that the LR has on the amount of product that can be produced. So now, how much of the excess reactant is left over? So that's the part we didn't finalize right here. Who's in excess again? Iron's in excess. How much do I have of iron? That, right? How much do I need of iron? I didn't finish it. So, can we figure out how much we need of iron right now? How do I figure it out? Using the half of copper 2 nitrate, how do I figure out how much I need of the other? No.
Multiply
Multiply by what?
by the half iron.
By no, not by the half of iron. So do you see how we took the half of iron, we multiplied by the ratio to figure out what you needed of the other reactant? We're going to do the same thing, but different, yeah. The LR, right? So I'm going to take my LR amount, I'm going to multiply by that ratio of iron over copper 2 nitrate. What's the ratio? 2 moles of iron, that's from the BCE, per 3 moles of copper 2 nitrate. And I'm going to squeeze it in here, guys. This is going to be how much I need. This is how much I need of iron to fully react with all of my LR. So what is that when you get there? .0017 moles of iron. Okay, so I have that much iron. I only need that much to fully react. So you can tell I'm going to have excess because I need a lot less. Yeah? So then how do I figure how much excess I have? That's when I do subtraction. So I have that much. I'm going to rewrite that down here. C 0.06446 moles of iron. That's how much I have. And I'm subtracting how much I need, which is 0.0017 moles, to figure how much I have left over. So that's why it's really nice to label your haves and needs, because that way it's easy to find it in your math. So how many moles are left over? 0.06276 moles of iron. Okay, what if my question had said how much well, much usually does mean mass. So what would I do for this last step? After I get my moles of iron left over, how would I get to mass?
The same process we did before.
So multiply by,
The ratio.
no, I want to go to mass. I'm just simply asking for grams of iron.
Oh, didn't we do the 500 grams of iron?
So that's that number. Thank you. 50. I wanted to look at the periodic table and tell me that. So 55.85 per mole of iron, and that would be that would be 3.5 grams ish of iron left over. 3.5. So you're like, throw the pencil down, I'm done. Drop. It's very sad. That's how you do an LR problem. It's not really that difficult, I don't think, and I think you'll see it's a lot of similar stuff we've been doing. It's just the thought behind how to start. So can we whip this like one more time? You tell me exactly how we did this? It's nice to revisit it after you have it done your paper. Okay, so what was the first thing we had to do? First thing we did. Very first thing. I heard BCE, thank you. Second thing. Okay, so how did you find the limiting zone? You went to what unit? Moles of both reactants, and then you compared them how? Multiply by ratio, halves, and needs to figure out how much you needed of the other one, and that's when you figured out, oh, I need a lot more, I only got this much. That's when you figured out your LR was. And then, after that, you just had your LR. So there's where we got our half. We multiplied by the ratio to get the need. We have the half. We multiplied by the ratio to get the need. And we started with, so part 2, we started with the LR moles. And that's really, that's all the mess gets you here. And then you had to figure out what the answers were from there. The last step was just taking the amount of excess based off your 2 different numbers to get how much you had left over. Okay, so I'm going to show you this, and I want you to put it in a chart form now. This is called a before, during, and after table. So again, just at the very bottom of your paper, write down your reaction again. What was the reaction BCE? 2Fe plus copper 2 nitrate yields. It's 3 of those, thank you. 2Fe. Okay, so leave some space, you get it kind of spaced out, and then this is what some people like to do. So before the reaction, how much do I have? You guys have these numbers down, I'm not calculating anything new. How much do I have of both of these? Point, is this iron you're telling me? Point what? 446 moles, okay? How much do I have of this one? 0.00255 moles, okay? And I have 0 of products because before the reaction, nothing's happened. So B means before, okay? During the reaction, who is getting 100% wiped out? The copper 2 nitrate, right? Because we previously figured out that was the LR. Here's how I tell some more advanced students, if this is you, if you want to do it this way, I'm fine with it if you understand what you're doing. The way I figure out the LR, as I do it all in my head, take the number of moles of the copper 2 nitrate, divide it by its coefficient. You got it in your head? It's something small, right? Take this one, divide it by 2. Which number is smaller? You can estimate. So 0.00255 divided by 3. That's approximately like 0.001, maybe a little lower. Take 0.06 blah 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 divided by 2. That number is bigger, isn't it, than this one? I'm not even like literally calculating it. I'm just estimating it. So right then and there, I said that one's my lower number. That's my LR. I didn't have to write down the have and need. I have my haves because I figured it out earlier, but I did not actually write down my needs. So that's just simply dividing by its own coefficient. Whoever's less is your LR. This is an advanced method. Once you figure that out, you know this one's going to be subtracted. You know every bit of that is going to go away. So I'm subtracting that 100% because this is during the reaction. Because after the reaction, how much of the LR do I have left? After the reaction? 0. That's the goal. I don't know why I wrote that so high. So after the reaction, I have 0 left over. 0 moles left over. So how much of this iron actually is reacting? I know there's going to be a number down here. I know there's going to be excess. But how much is left? And this is where I actually use that ratio, but I'm writing it in math form. So I'm subtracting the LR amount. I'm subtracting 0.0025. But in a ratio of iron to LR, in a ratio of 2 to 3. So iron to LR, copper to nitrate, is a 3. So this right here, where's that on your paper previously? Find it. Find 0.00255 times 2 over 3. That's the need. I'm literally right in the table saying this is how much I need of the LR to react with the iron. Or I'm figuring how much of the iron I need to react with the LR. So I'm actually doing that in the table form. So tell me, when you subtract 0.006446 minus this mathematical calculation, what do you get? Same as you got in part C, right? This here is this here. 0.062276 or whatever it was, moles. And that's excess, that's leftover. So all I've worked with so far are the reactants. I haven't even touched the products, but I'm getting ready to. So if you like this so far, then keep up with me. If you're not, if you're like, I got the other way, good, just ignore me right now. So for the 2 reactants, the one I was questioned on was copper. So I start off with 0 of copper. The LR, which is this number here, is controlling how much copper I can make. So I'm adding copper because you create products. So I'm adding 0.00255 in what ratio? 3 to, I'm going back to LR number every single time, 3 to 3, right? So I'm looking at my copper here, which is a 3, over my copper to nitrate, which is the limiting one, which is a 3. So that's just 1, right? So that's why when I decided I'm making this amount of copper. And that's in moles, but the question actually for us, in that question it asked us to go to grams. So what we do here, if I want to go to grams of copper, so times it by 63.55 grams per mole, and that would give me grams. That would give me what we got in part B. So that would give me 0.162. See? 0.2000225 times 3 over 3 times the molar mass. Who's seeing the similarities between these two methods? Some of us are liking it, right? So whatever that was. So you can choose. If you understand how to do the BDA table, it's called before, during, and after reaction. If you like this, it's very organized. I like this because I'm an organized person, try to be organized. Then I go with this. If you like the have-need method, where you draw it, write it out, then go with it. It's your choice, but be proficient, whichever one you choose. Okay, so we have about 20 minutes left. You guys have problem set 12 with you? Okay, I would like for you to work on that and get my help as needed. All right, let's get her done. Oh, I'm not doing the other one. Oh, another joke for you. Stoichiometry. Okay.